Okay, so let's do, you want to do searching or sorting first? Crowd's choice. You want to do searching first? Okay. I was almost going to do that first anyways. But. Okay, so we've introduced this idea of a list, right? And remind me, what's kind of maybe some of the features of a list compared to a string? What's nice about a list compared to a string, maybe? Let's just kind of...
Values are kind of individual, so you can mess with them and change them.
Okay, yeah, it's the changeability is really the thing, right? So we can kind of think of a string as being like a list of characters. That's fair enough, right? But it's just kind of like a list of characters, okay? We could say it's hypothetically a list of characters, but the difference is you cannot change the contents of a string. Instead, what do? We build a new string, right? But now lists are read and write. So we could create a list of characters. In fact, before our exam, we had written I think a function that converted a string into a list, right? So we took the contents of a string, looped through everything in the string, filled up a list with the exact same contents, and now we can go and we can change what was at bucket 3 in that list into something else. We can put a question mark there, whatever, overwriting what used to be there. Whereas strings are read-only. If we want to change some aspect of a string, we have to build a brand new string, keeping everything that we didn't want to change and then making that one modification as we're building the new one. Okay, so lists are read-write. With that now comes some advantages. Well, maybe not advantages, comes some new abilities. Okay, one of these abilities is now we can manipulate lists, and we're going to see that when we get into sorting. Okay, but now let's say I give you a list of numbers. That's typically when we're searching for something. You know, the starting point might say you have a big list of numbers and you're searching that list of numbers. Okay, now let's kind of figure out how we might do this. You know, we grow into this. So let's say I hand each of you a kind of like a deck of cards, but on each of those cards is written one number. Okay, and I say find 5. What are you going to do? Give me one possible solution to finding the number 5 in a stack of 30 cards. Good. Okay, you could certainly throw it into the air and then what, crawl around and... Oh, while it hits... Okay, so more of like a magic trick type thing.
I couldn't do it.
But it's hypothetically, it could be... All right. How else might you search for... you know, what's the simplest way if I give you a stack of cards with numbers on them? What's the simplest way you might go about if I ask you, is there a 5 in there? Yeah, flip through each one, right? One at a time. Okay, so start at the beginning, go all the way to the end. Okay, so that's something that we call a linear search. All right, now something you're going to talk about kind of eventually in one of your courses. I just touch on it in here. You'll probably actually get into this is actually the real good word of theoretical. The theory behind this is there's this idea called big O notation. It may have even been mentioned in the book so far. Has the book mentioned big O notation? Or order of magnitude? Okay, 2 kind of scary phrases. All that really says is, you know, how efficient is a specific algorithm. All right. Now, right now we're beginning programmers. We're not all that interested in efficiency. All right. We're interested in correctness, or even mostly correct at this point. All right. Efficiency's out the window, so we're not going to spend a whole lot of time talking about efficiency, but we have kind of a notation in computer science for generically describing the efficiency of an algorithm. All right, and typically, and it's called big O notation. Typically, what you're really giving there is the number of comparisons that have to be done in order for something to succeed. So you might even dumb that down one more step and say, how many if statements have to occur on average in order for a particular algorithm to finish? So in a linear search, what's the best case scenario if you're looking for a 5? The very first card you flip over is your 5, right? 1. Can't get more efficient than that. What's the worst case scenario? If you have n cards, it's the last one. So if I give you 30 cards, n cards, it takes you 30 checks to either find it as the last card, or if you didn't even find it, it was, like I checked them all, not there. So, you have the big range. We would call that order n. Okay, that guy would be order n. As a worst case scenario, it's going to take you checking all of the cards to see if you find them in there. That's not considered very good. Okay, but remember, computers are fast, so kind of who cares, right? Let him do all the searching. We're not the one flipping through the 5 million cards. The computer can do it. We don't care if it's extra difficult for the computer. All right, so linear search says, search each element in order. And we have a couple of different versions of this. I might ask you a question. So when I have you look through a collection linearly, I might say, is the value found? True or false? Okay. So you might flip through. I might say, is there a 5 in that stack of cards? Kind of like the game Go Fish. Do people play Go Fish anymore? It's still a thing. Like that's like a game you play when you're like little. Oh well, I still play it. Minor leagues, somewhat competitive. Okay, but you might say, okay, is there a 5 in your stack of cards? Right? You flip through. If there's a 5, yeah, I got one. You might have 3 or 4. You don't know. Once you hit 1, you say, I got one. Right? Okay. Now that might be the question you're asking with linear search. You might also be asking, if you have a collection of cards that are in no particular order, you might say, where is the first occurrence of a 5? Okay, so if you index the cards bucket 0 through bucket 29, if you have 30 total cards, right? You might say, oh, I found my first 5. There might be more, but I found the first 5 at bucket 11. Okay, so you might be interested in where in the collection of cards did you find it. Both of those are still linearly searching through the collection. Make sense? So a linear search, this is our easiest search. So let's go here and let's, do I have that guy? What are we using? We're using Adam in here. Telemetry consent. No, I want to keep seeing that. It's kind of makes my day sometimes. All right, so let's go ahead and we're going to write a linear search. And why don't we go ahead and write the first version of is it found? So maybe we'll call this guy is found linearly. Yeah, good enough. All right, so we might say def is found linearly. All right, and we're going to take in a value that we're searching for, and then a list that we're searching in. All right, we need those two things. So I'm going to hand you your deck of cards. I'm going to say look for a 5. Make sense? Those are the 2 pieces of information this guy's going to need in order to search stuff. Now, we want to go through every single element in that list. Now, up to this point, I'm going to go ahead and I'm going to show you a for each loop here because I think I had mentioned last time we wrote something. I said, did we look at for each loops yet? And somebody said no, so I did it with the counter. So up to this point, what have we done? We've gone through bucket 0 up to the length -1 of our lists, right? So let's do it that way first, and then I'll convert it over to our a for each loop. Okay, so we're going to have a variable called pause. We'll start that guy off at 0. Actually, we can do this as a for loop in this case. So we'll say for pause in range. And the first element in our list is bucket 0, right? The last element in our the last legal bucket is, what is it, list dot, no, it's the length of list, -1. Okay, but remember, range is non-inclusive. So 0 to length of list gives us 0 to length of list -1. That's the indexes it'll give us, right? Okay. Okay, and just as a quick, I'm going to kind of take advantage of us writing some of the stuff to kind of show some of the things that people commonly missed on the exam. So I'm going to go ahead, not even writing any real logic here. I'm going to go ahead and I'm going to print out pause here. Okay, just so you can see what the value of pause is. Because what this code right here is doing is it's taking pause, which is just a number. Okay, so pause starts off as 0 and goes up to, if our deck of cards had 30 things in it, goes up to 29. Go ahead.
Why are you wanting to not include the last value?
This will include the last value of the list.
It would.
Yeah, because length of list is 30. Range gives us this value non-inclusive, so this will be 0 to 29, which covers all 30 buckets. Does that make sense? Yeah. It's not that I'm not including the last one. It's a 0 index list, so the last bucket is actually one smaller than the length. Go ahead.
Could you use, like, for example, for pause in list, like using that way instead of?
That's the for each loop. I'm going to show you in like 5 minutes or something like that. Yeah. But I'm also, the reason I'm doing it then is you're going to see that the for each loop is convenient sometimes, but doesn't give you what you need other times. Okay, and because we're going to write this twice. The first one we're doing is the return true or false. Is it there? Which the for each loop would be great for. The where is it one, we're going to see there's a weakness with the for each loop. So that'll give us an opportunity to look at that. But for right now, well, all I want to explore here is what does this loop do? This takes this variable pause, which appears to be holding a number for us, right? On a voyage between 0 and the length -1. So that'll be 0, then 1, then 2, then 3, then 4. That's all this loop does. It happens to count based on the length of our list. Right now, we're not even looking at the variable val, okay? But what a for loop does is takes this number on a voyage between 2 points. What we do with that number inside the loop is completely up to us. That's where our logic comes in. But this for loop itself just takes us on a loop, just takes us on a voyage between 0, then 1, then 2, then 3, then 4. And we can do whatever we want with it. Right now, we're just printing it for no good reason. Okay? So I'm going to go ahead down here, and we're going to call our is found linearly. And I'll pass it a 5. And I'll go ahead and pass it the list. Whoa, I missed the comma apparently. The list containing 5 elements. So the length of that list should be 5. The legal bucket should be 0 to 4. That makes sense? So that's what I'm passing to is found linearly. Passing it a 5. Passing it the list containing 5 elements. Right now, I'm not even using that value 5. And this loop is going to say pause starts off at 0, goes all the way up to and including 4. Print out 0, print out 1, print out 2, print out 3, print out 4. That makes sense? That's all a for loop is doing. I want to be clear that this for loop is not connected to the contents of that list. Only if we choose to use that index, only if we choose to use pause to index into the list, do we actually connect it back to the list. Okay, this loop itself is only loosely even related to our list because we built our range off of the length of the list based on how many elements were in the list. But inside here, we're not taking advantage of the contents of the list at all. Does that make sense? Okay, so there was a clear misunderstanding for several people on the exam, whether it was strings or lists or whatever, that somehow this for loop is very much intertwined with strings or lists. And it's not. This is just for counting. And if we happen to use those numbers to work with a list or work with a string, that's fine. Okay? So this should give us 0 through 4 just printed to the screen. That's what this guy should give us. So let's go ahead and run this. Okay. Oh, he rejected that? So there's our 0 to 4. That make sense? Okay. Now, we don't want to print out 0 to 4. Instead, we want to search for elements inside the list. Well, let's take it one step further. Let's now use that integer to access a particular element in that list. So instead of printing out pause, let's go ahead and print out list at position pause. Now we are starting to marry this loop to the list. We're actually working with the list as part of that variable from the loop. Okay? So this should print out a 1, then a 2, then a 3, then a 4, then a 5, because that's what I put in this list. If I want to change it up a little bit and something like that. Now it won't look as linear, right? Because the values of this list are then 14, then 21, then 3, then 74, then 15. Each time through this loop, I'm taking the current value of pause and I'm saying, give me the value in the list at that position. Okay? So this should print out 14, 21, 3, 74, 15, because that happens to be the value I'm passing in there. Keep in mind that if I call that same function another time with different parameters, doesn't even matter what I passed there. So now this is a list with only 4 elements in it, and the values are 7, 2, 13, 12. All right, I'll put a little print in between here, just as a separator, so we see the 2 different calls separated. So I've written this function one time, and it's written generically. It operates on whatever list we pass it. Okay? The first time I call it, I'm passing it this list. The second time I call it, I'm passing it this list. I'm applying the identical logic to 2 different inputs. Okay? So first time we run this, it should print out 14, then 21, then 3, then 74, then 15. Then we should see our separator. Then it'll print out 7, 2, 13, 12. All right, so there's the contents of that first list. There's the contents of the second list. Okay. Now, what we're trying to accomplish here is not printing out the contents. Instead, we want to return true if we find the value that we passed in, the value that we were looking for, and return false otherwise. Keep in mind, return and print are not the same. Okay? So let me go ahead and let's write it the wrong way first, where we'll print out found versus not found. Okay? Then we'll actually return it and see the difference. So what I'm doing is I want to loop through every element in list, and I want to ask the question, is the current element I'm looking at equal to the guy I was looking for? Okay? So we'll ask a question here. We're going to say, if list at position pause is equivalent to the value we were looking for. If that's a true statement, then let's print out, we'll just say print out found for right now. Okay? And just as a, I'm going to go ahead and do this, just so we can see the dynamics of this. So as I loop through here, if I'm looking at a current value that's equal to the value I was searching for, I'll print out found. Otherwise, I'm going to print out keep looking. No matter what happens here, I will look through every element in my list, whether I've already found one or not. Okay? And so let's see. Let's go ahead and let's search for a 74 here. So we know it'll be found. Okay, so I'll search for a 74 in that guy, and we'll go ahead and get rid of this. So the first time through, this is not the 74, so we're going to see keep looking, keep looking, keep looking, found, then another keep looking. That make sense? That's what the output of this guy is going to be right now. This function is not returning a value yet. It's just printing a bunch of stuff as it's going through. And that's okay, especially when we're learning how this stuff works. You sometimes want to kind of see the logic as we're going through it. Okay? Next semester, when we get into the Java stuff, I'll introduce you to the debugger in the tool that we'll be using for Java called Eclipse. There is a debugger for Python, but it's not very friendly to use. So let's not destroy worlds with it right now. But that allows you to walk through your code line by line by line without putting a bunch of print statements in there. Okay, but for right now, print statements are fine. It helps us kind of visualize what's happening at different points in the function. So we expect this to be keep looking, keep looking, keep looking, found, keep looking. That's what the output of this guy should be. So there's our keep looking, keep looking, keep looking, found, keep looking. Okay? Now, certainly, we wouldn't have wanted to see another keep looking after we finally found what we were looking for, right? We wanted this guy to end. All right? So, we need to look at how do you get out of a loop if you want to get out of a loop. All right? If you want a loop to end, how do you do that? So once we find it, I'm going to go ahead and I'm going to put in here a keyword called break. Break immediately causes the loop you're in to end. It does not cause the function to end. And let me show you that. So I'm going to come down here and we're going to do print outside of the loop, or maybe after the loop, but whatever. Okay? So we will get to this line as soon as this loop ends. Now, right now, so let me go ahead and we'll comment that out for a second. Right now, what we would see is we saw keep looking, keep looking, keep looking, found, keep looking, then we would see outside the loop. I'll go ahead and run that. So there's the three keep lookings, the found, keep looking, and then we finally, the loop has terminated naturally, right? We've run out of pauses to check. The loop has ended, and now we're outside of the loop. But really, after we found it, I'd like to get out of this loop. I want this guy to end. But perhaps I'm not done with my function. In this case, we are, but not yet. We haven't written that code yet, okay? But perhaps we're not actually done with our function, and we want to just get out of this loop and keep doing more stuff. So we can do a break here. Break says immediately escape out of the closest loop. Okay? Get out of the closest loop. Put that into our notes here. So the break keyword says immediately exit the closest loop. Okay? So now what we should have happen with this break is we will see keep looking, keep looking, keep looking. Finally, we find the value we're looking for since we're looking for a 74 in this list. And then we're going to break out. And the next thing we'll see is outside of the loop. So we won't see that final keep looking. We did not naturally exit the loop. We short-circuited the loop. We dove out of it early because we were done doing what we needed to do. So there's our found, and now we're outside of the loop. That make sense? Now, in this case, I said that what we want the is found linearly to do is we wanted to return true if the value we were looking for was found and return false otherwise. Okay? It's not printing. It's returning a value. So in this case, if we found the value we're looking for, we're not printing anything here. Instead, we're going to say return true. I'm going to leave this break in here just for a second because I'm going to ask you a question about these. We're not even going to have an else. Because we're going to continue to look, but we're not giving any visual feedback here. What we're doing is we're spinning through every element in our list. If we found the value, we're going to return true. Now, if I've run out of stuff, that is my for loop naturally exits. That means I never found it. I almost think of this as like a minefield. Okay? If I was running through the field and I never stepped on a mine through here, that means I never returned true. So if I'm still kicking after this for loop is done, that means I didn't find it. Go ahead and return false. That makes sense? So now, based on what we already knew about return, what's the difference between return and break? Go ahead.
Return will actually end the current function, whereas break just ends the current loop.
Correct. So return makes the current function, wherever you are in that function, makes it immediately end. You can optionally return a value. For instance, I've said that what we want to do here is return true if we found it. That's why I've put return after this guy. But that's legal. I can just say, I'm done. I've done what I came here to do. I want this function to end. Just put the return statement there. That makes sense? So return makes a function immediately end. Break makes a loop immediately end. Understand the difference? Just for completeness here. This was assumed to be happening here, but I went ahead and put this else back in. A third keyword that we can go ahead and introduce right now is the keyword continue. Continue says stop the current iteration through the loop, no matter where in the loop we are. Okay, if we're the first question in the loop and there's 7 other lines of code after that, immediately stop the current iteration of the loop. Go back to the beginning of the loop and go on to the next iteration. So if we were currently with pause is equal to 3, it says immediately go to pause is equal to 4 and start the loop again. Okay? So it skips this iteration through the loop is what continue does. The reality is I didn't have anything else to do inside the loop here anyway, so I was already skipping to the next iteration through the loop. But continue forces that. Okay? So the continue keyword immediately skips to the next iteration of the loop. Okay? That's what continue does. And sometimes that's helpful. Sometimes you might have 30 lines of logic, and at line 4, you've decided, okay, well, I'm wasting my time doing the rest of these this time through the loop, but I'm not done with the loop yet. But let's go ahead and let's short circuit the loop and jump to the next iteration through it. That make sense? So we have another keyword, another tool, continue. In this case, continue is a waste of time because the loop was naturally doing that anyways because we had hit the end of our logic. All right, it wasn't wrong. It would behave identically, but we were, telling it to go ahead and do what it was going to do anyways. So now, if we found the value we're looking for, we're going to go ahead and return, which makes the function immediately end, and we want to spit out a value. We want that return to come with an output. Okay? This is not printing anything at this point in time. All right? Otherwise, we're returning false. So if I were to run this program right now, even though I'm calling isFoundLinear, I'm passing it my number, I'm passing it my list, we happen to find a number, so we know in this particular case it's going to get to this return true. If I was searching for a 75 in that list, we know it's going to search the whole list, not find anything, so it made it through the minefield and it's going to return false. What I'll visually see as output to my program will be nothing, because I never actually print a value. I've returned the value. I've never displayed it. Oop. Oh, true and false not defined. Are they capitalized? Okay. Program ran fine. Just let me show you what I did real quick there. In Python, remember I said that languages are case sensitive. So the true Boolean constant starts with a capital T. The false Boolean constant starts with a capital F. I want to say in Python 2, it's lowercase, but whatever. The interpreter yelled at us, we fixed it, and life goes on. All right, so this is the Boolean constant true. This is the Boolean constant false. But we notice here that our program had no output. We had no errors, but we didn't actually print anything. Instead, we returned a Boolean value of true or false. What's a Boolean expression again? Any expression that boils down to a single value of true or false. So we could ask a question here. We can say if is found linearly, passing a 75 and this, we can go ahead and say print out not found, or print out found rather. And then if we wanted to, we can do an else. Print not found. Okay, so now I'm calling this function. And everything I have highlighted there will ultimately boil down to what? A single value of true or false. Because when we look inside of this function, even though there's several lines of code here, we see that our return statements give us either trues or falses. So even though this looks like a function call with two different parameters, one of them is a list, that stuff that's highlighted there will either be a true or false when all is said and done. So that guy's a Boolean expression. So I'm asking a question about that. I'm saying if this function ultimately boils down to true, go ahead and print out the word found. Else, print out the word not found. I'm making a decision based on the output of that function. The function itself is not printing things. Does that make sense? The difference between printing something and returning something? Now our program will have a visual output because I am acting on the result of my function by asking a question related to it and then actually printing something. Oh, that was my slash. So not found for the 75 in that list. If I come in here and I change it back to a 74, which we do see in the list, we should see a found this time. And there's our found. That makes sense? Okay. Oh. Now, I mentioned that I was going to show you a for each loop. Right now, we're utilizing this knowledge that lists are indexed from 0 to length of the list minus 1. So we happen to be using our for loop version that takes a integer on a voyage between two values. But we could instead do something like for list val in list. if list val is equal to val, and we could have called this whatever we want. We could have called that dog if we wanted to. That's just a variable I've chosen. List val being the value of the current value we're looking at in our list. So this takes this variable list val on a voyage. Each time through this loop, list val will be the next element in the list. We no longer have access to the index where we are. We don't know if we're at bucket 2 or bucket 3 or bucket 4. All we have is the next value, the contents of the list. That makes sense? So as of right now, this code does identically to what it did before. We just happen to go through our list value by value by value rather than going through a bunch of integers and then using that integer to grab a value from our list. So we'll go ahead and run this again. There's our found. If I change this back to a 75, we'll get a not found. And let me just quickly cut this stuff out. And I'm going to go ahead and I'll print out list val in here. That should be okay. Oh, it's not actually what I want to do. Just so you see what this does. This for each loop, that's what I would call this, is a for each loop. For each list val inside of this collection, inside of list, print it, print the value. So we should see the output 14, 21, 3, 74, 15. Oh, I still had the end of my if statement in there. There's my 14, 21, 3, 74, 15. All right, so let's go back to where I had everything still in here. All right, so as of right now, that guy does the same thing our other code did. And just as an example, this for each loop works with any collection. So I can say, let's just call this guy print string, have it take in an S, and we'll say for char in S, or here, we'll just say for C in S. That's each character inside of S. Print C. And then what I'll do here is I'll do print string hello. Or let's comment these couple of things out. It's probably going to give me an error because I bet you it requires you to have something after the for loops or the if statement. So we'll just do that. So we'll see that print string is passing a string in, which is like we talked about at the beginning of class today. It's kind of like a list of characters, except it's read-only. So we can't change an individual element, but what we can do is I can take in a collection of characters and I can go through that entire collection and set C equal to each individual character. So now I'll print out an H, then an E, then an L, then an L, then an O. Rather than having to grab the character at position 3 in S, I'm grabbing each character in S. That makes sense? So there's the contents of hello. Now understand this actually is not in Python, this is not a different kind of loop. The reality is in Python, all for loops are for each loops. Because what have we been doing with that range function? We've been generating a list of numbers, right? We've been generating a collection. So every loop we've written up to this point has been a for each loop. We just didn't really advertise it as that. In other languages like Java, there is a distinction between a counting loop and a for each loop. Just slight, they look pretty similar. But you want to use the right tool for the job. One of them is not necessarily better or worse than the other. In this particular case, since we only care about the values and we don't care about where we are in the string or where we are in the list, a for each loop is perfectly convenient. Might as well use it, right? Okay. Now, let's go ahead and see why a for each loop might be a little bit of a problem for us. A little bit ago I mentioned if we're going to do a linear search, if we're just interested in whether or not a value was found, we might go ahead and choose to use a for each loop. But what if I'm interested in where in this list the first value was found and I'm going to search through it in a linear fashion? We've actually written this one before, right? We wrote our own version of find, I believe. Did we do like an index of? Did we write that in here? Where we search through every element and it returns a -1 if it's not found? Yeah, I think we wrote our own version of that even though we had it with find, correct? So if I have a string hello and I asked for the position of the E, it would give me a 1. If I asked for the position of the L, it would give me a 2, even though L is found at 2 and 3. It would return the first legal position of it. If I asked for the position of a Z, it would return a -1. So we're going to go ahead and we're going to modifier is found linearly to return that position. So instead of saying if list val is equal to val, well, we'll still say that, but instead of returning true, we want to return the position inside of list where we found that. And the problem we have right now is we don't have that position. We have list val. We have a character, a value inside the list. Actually, in this case, it's a number because our lists that we had down here were numeric lists. All right, so we're going to look through every character in list. If it's found, I want to return the position where we currently are. Where did I find it? And using a for each loop like this, we don't have that position. We only have the character. Now I could hack this a little bit, and I can go ahead and say, okay, well, I'm going to have a variable called pause. And we'll start pause off at 0. So once I find it, I'll go ahead and return the current value of pause. Regardless, I'm going to say pause is equal to pause plus 1. So I'll always add 1 to pause as I go through here. So I'm kind of keeping track of where I am in my list alongside of this for each loop. That make sense? So not the end of the world, but you can see that we had to, and down here I'll go ahead and return a -1 if it wasn't found. Okay, so as we go through this guy, we're artificially keeping track of where we are so that when we do find a match, we can return where it was located. And I'm printing that out. We're looking for a 75, so this should give us a -1 right now because it was not found. If I change this to look for a 74, this is 0, 1, 2, 3. It was found at bucket 3. So there's my 3. Now if I go ahead and I add another 74 onto the end of this guy, now 74 actually exists twice. Okay? So since it exists twice, my current code is going to print out the first place I find it. Not the last place. That makes sense? For your homework assignment, modify this code to print to find the last position in the list where something was found, or -1 if it was not found. So modify it such that the 74 won't return a 3, instead of return a 5. The last place it found it in there. That make sense? All right, so should be a slight modification of this. I'll go ahead and post the current code up to Slack. Oh, and just so you're aware, there was a second page of students, so some of you are missing 4 grades. Okay, your 4 last assignments. In Blackboard, there's a little button at the bottom that says next because there's so many students in here. So basically, a good portion of the class, I've graded everything, and then some of the class, I haven't graded your last 4 assignments because it's on that second page and I've ignored it. So I'll catch up with that today. All right, so if you're missing your last 4 assignments, you're in that group, you'll see your grade by, I don't know, 2 p.m. or so today. Midterms are all recorded, but it was those 4 assignments because I do midterms on a different screen.